Welcome to this video on logistic regression. In this video, we will talk about how do we interpret the coefficients of a logistic regression, and we will also talk about how do we estimate or forecast the likelihood of the dependent variable being a 1, the probability that it is a 1, given a set of values for the independent variables. Let's start with a recap of what we had learned about logistic regression. In the prior video, we had discussed why we can't, or at least shouldn't, use linear models when we have a binary dependent variables. We had found that our forecast would be outside of the range of probabilities that is from 0 to 1. To fix this, instead, we use a logistic regression model that looks as follows. We have the log of p over 1 minus p as dependent variable, and the remainder of the expression looks like a linear model. If we call that expression y star and simply rewrite it, then we end up having something that looks very familiar to us, a linear expression. And there are actually several similarities between linear models and logistic regression models that we can leverage on. For instance, if we have the output of a regression where our dependent variable was subscribe, and subscribe indicated if a customer subscribed to a given magazine or not, and we find that the coefficient for age is positive, we can use this to say that as customers grow older, customers are more likely to subscribe to the magazine. We can think of this as a magazine that is targeted towards more elder people. We also have at our disposal the standard errors. And as we did with linear models, we can use the standard errors to compute confidence intervals for the coefficients. In the case of age, we have that the coefficient is 0.781, so we can add and subtract 2 times the standard error of 0.0535, and we end up with the confidence interval for the slope of age that goes from 0.674 to 0.888. However, this is as much as we can do if we think that these are similar to linear models. What has changed? Well, the most important change has to do with the interpretation of the magnitude of the coefficients. In particular, in our prior model, what would the meaning of 0.78 be if our model has as dependent variable the log of p over 1 minus p? Well, if we think in linear terms, we would say that for every unit increase of age, then the log of p over 1 minus p, the dependent variable, increases by 0.78 units. But what exactly is the log of p over 1 minus p? The coefficient really makes little sense to us, and we don't really know what a 0.781 increase in that particular metric implies. Now, remember that we had called this y star as well. And let's see if we can convert this y star into a p. So we have that y star is equal to the log of p over 1 minus p, which in turn is equal to the expression of the beta zeros and the x's, the independent variables. If we recall how we had transformed the probability to make it something that is bounded between 0 and 1, we had that the expression of the beta times x's over that same expression plus 1 was equal to the probability. Or simply put, since that expression is equal to y star, we can say that p, or the probability, is the exponent of y divided by the exponent of y plus 1. And it looks complex if you look at it on the big picture, but if you take it step by step, it is very simple. I am now going to show you an example in Excel in which we convert the y stars into probabilities, into p's. What I am showing you now is an Excel sheet with the transcription of the coefficients we got from estimating our model. Specifically, we have estimated that the constant term is a negative 26.524 and the slope for age is a positive 0.781. So these are the betas we got from running our model. What we're going to do now is plug in some independent variables, some x's, to estimate, for example, the likelihood of a 35-year-old customer of subscribing to the magazine. So since we're going to be multiplying the coefficients by the x's, let's, for example, compute this for a 35-year-old person. I'm going to multiply the constant by 1, and the age coefficient, I'm going to multiply it by a 35. So now we simply perform the sum product of the coefficients, and I'm going to lock in these values so that we can multiply them by several sets of independent variables. I'm going to multiply the coefficients times my x's. We get a 0.81. Is this the probability of a customer that is 35 years old subscribing to the magazine? I'm going to let you think about this for a second. If you recall, what we get out of the logistic regression is not a probability. It was the term we called y star, which was equal to the log of p divided by 1 minus p. This is not the probability, but how do we convert this into the probability? Well, we also discussed how the probability is the exponent of y star divided by the exponent of y star plus 1. So what we must simply do now is compute this formula, and I'm going to do it right here. I'm going to say that p is the exponent of the value I found for y star divided by the exponent of y star plus 1. Okay, I'm going to hit enter. And now we have found that the probability of a 35-year-old customer from subscribing to the magazine is 69.3%. And this is very nice. Now let's see what happens at this age range if the customer grows 1 year older. That is, let's estimate the impact or the probability of a customer that is 36 years of age from adopting or subscribing to this magazine. I'm going to have a 36 here, and I'm going to simply drag our formulas. Note that my y star now increased to 1.594, and the probability of this customer subscribing went all the way up to 83%. If I compute the change of this, I found that the probability increased by 13 percentage points, which is quite a bit. Now let's do a different exercise. We had also seen the example and computed the likelihood of a customer with 25 years of age from adopting. And I'm going to put 1 and 25, perform the same exercise. The probability of this customer adopting is very small, so much that we're using scientific notation to tell us that this variable is very close to 0. At this level, if we grow by 1 year in age and have a customer with 26 years of age, the probability is now greater, but how much greater? How much did it really change? Minimally. Note that when going from 35 to 36 years of age, the probability grew 13 percentage points. Meanwhile, the probability of going from 25 to 26-year-old only grew by 0.1 percentage points, much less. This is because the logistic regression is representing a relationship that is not linear. Now let's go to the other extreme, to the older customers, and check what happens if we have a customer that goes from 45 years of age to 46 years of age. I'm going to have ones here again, 45, 46, and I'm going to drag my formulas. Note that in both of these cases the probability is already a 1. If we compute the change once again, there's no change in the probability, or at least it is very small. There's no difference in the likelihood of subscribing if we grow from 45 to 46 years old. So we're finding evidence that this relationship is nonlinear. Growing 1 year older does not mean the same if you are young, if you are mid-range age, or if you are old. What we have just seen in numbers is nothing more than the plot that we had seen before, where at the lower bounds of age, say near the 25 years of age range, the probability is low and doesn't change much. A similar thing happens at the upper range of ages, say around 45, where the probability of subscribing is high. However, the change from 45 to 46 was not really meaningful. Most of the fun, most of the change really happens around the middle, around that 35 years of age range, which we also analyzed. Moving from a simple regression model with a single independent variable, in our case age, to a multiple regression model with more than one independent variable, we're going to be using age and gender, is actually very simple. Let's simply add a dummy variable to represent gender and run a model that has y star equal beta 0 plus beta 1 times age plus beta 2 times our dummy variable to indicate if a particular observation is a woman. We're going to use this as our multiple logistic regression model. We run it in a statistical package such as Gretel, and we find that our estimated model has the following form. We have an intercept of minus 26.47. The slope for age is a positive 0.79, and the slope for women is a negative 0.56. So as we did before, we can interpret the signs of the coefficients and compute confidence intervals. In particular, in this case, we find that age continues to have a positive effect on the likelihood of subscription, which means that this magazine is designed for older people. And at the same time, we have discovered that it is less likely that a woman subscribes than that a man subscribes, which means this possibly is a magazine designed for men in higher age ranges. However, we want to convert this into probabilities. We want p's. So now we're going to do the same process we did before of estimating p's or converting y stars to p's in Excel, but for a multiple regression model. We are now going to follow a similar process as the one we did before, where we first transcribe the estimates for the coefficients and then plug in independent variables values to predict probabilities of subscription. Specifically, in this case, I have transcribed the constant term, which is a minus 26.46, the coefficient for age, which is a 0.7872, and a coefficient for women, which is negative, suggesting women are less likely to subscribe to the magazine, and the coefficient was minus 0.5578. So let's estimate the likelihood of a 35-year-old woman subscribing to the magazine. We're going to be multiplying the constant term by 1. We multiply the age coefficient by 35. And in this case, we multiply the woman coefficient by a 1, because that's the value for a dummy variable. Once again, to find the y star, we're going to multiply the coefficients by the covariates, the independent variables, the 1, the 35, and the 1. And this is the value we find for y star. And once again, remember, y star is not the same of the probability. The probability of this 35-year-old woman adopting is not 52.9%. We must perform the transformation where we take y star and use the exponent of y star divided by the exponent of y star plus 1. And now we find that the probability of this woman adopting or subscribing to the magazine is 62.9%. Let's now investigate, for instance, how would things change if rather than having a woman, we had a man, a male, and see how this changes for a 35-year-old male. We have 1, 35, and now we turn off the woman dummy variable. Note that the probability now has increased from 62% to 74%. Specifically, we have an increase in the probability of 11.9 percentage points. Now let's do another exercise. Let's, for instance, test what is the impact of one more year of age for each of the two genders. And let's look at a 36-year-old woman and a 36-year-old male. We're going to have ones here, 36 and 36. And here we have woman turned on, here we have woman turned off. I'm going to drag my formula. And note that the probabilities of adoption have increased. In the case of women, it went up from 62.9% to 78.9%. Meanwhile, for men, it went up from 74.8% to 86.7%. Specifically, the change in between genders in this case is only a 7.8 percentage point difference. Note that the difference is lower, once again suggesting that the relationships are not linear. The change in gender represents different things for 35-year-old customers than it does for 36-year-old customers. In class, we will explore in much more depth the implications of having a nonlinear model.